Okay, so now I'm going to talk about something called intermolecular forces. Intermolecular forces are forces of attraction that are between different molecules. Bonds are intramolecular forces. That's INTRA, meaning in one molecule. Intermolecular means they are the different molecules are attracted to each other through these forces. Okay, so I put them here in order of weakest to strongest. The first one we're going to talk about is London dispersion forces. London dispersion is also known as van der Waals, but I use London dispersion, which abbreviated LDF. Okay, they exist between all molecules. So the principle behind LDF is that electrons are constantly moving. That's something that I've talked about in my classes, and I'm sure your teachers have also mentioned. They're constantly in motion. Okay, so our molecules and atoms and all this stuff, constantly in motion. So at any given time, the electrons could all be on one side of the atom or the other side of the atom. So when we think of atoms, I'm doing a very basic atom here. When we think of atoms, we think of like a perfect circle. I'm not even going to try to draw a perfect circle because you all know from the last video, it's not going to happen. So we think of them as a perfect circle. But the truth is that electrons could be concentrated on one side or the other. So let's say our fake little atom here, at one point, it looks something like this. So in this one, this is me drawing the electrons. So this would be where the electrons are concentrated in this time, okay? Now this time is just a split tiny second, like so small that we really can't even really picture how small it is. So very small, tiny second of time. And for that very small, tiny second of time, this side has more electrons. So just like when we were talking about polarity, this is going to be slightly negative over here. And this side will be slightly positive. Okay, because it doesn't have the electrons. Now, the difference between this and polarity, I'm going to get to on the next slide, okay? So they are slightly negative and slightly positive. So let's say we have another molecule that has its electrons distributed like this. This side has more electrons, so it will be slightly negative, and this side has fewer, so it will be slightly positive. Okay? And then what happens for this very small, very tiny split second, these slightly positives are attracted to the slightly negatives. And again, I'm going to use a dashed line for my attraction to show that it's not a bond, okay? And then this slightly positive would be attracted to the other slightly negatives. And the molecules or the atoms are going to spin around and constantly, like, the positives will go near the negatives and the negatives will go near the positives, and then they'll move and then they'll go to another one, and so on and so on. So what you need to think about is that these LDF only last for such a small amount of time that's why it's the weakest force, okay? The nice thing is it's in everything, but you also have to keep in mind that it will be there only for a split second. Next, I want to talk about dipole-dipole forces. Now, dipole-dipole forces are between polar covalent molecules, okay? So polar molecules, that's a dipole. Remember, we learned that in the last video. In this, the slightly positive end attracts the slightly negative end, just like before. So if I draw a picture of this, it's going to look very similar to the last one. I'm just going to actually use um, this, CO. So CO um, looks like this. I'm not going to bother drawing the lone pairs. We don't need them for this. Okay. And we talked about in the last video, we know that oxygen is going to be slightly negative, and carbon is slightly positive. And then just like the last slide, the slightly negatives and the slightly positives are attracted to each other. So this slightly negative, this slightly positive, excuse me, will go over here to this slightly negative, and then this slightly negative will be attracted to this slightly positive, and they'll spin around, and there will be a whole bunch of CO molecules, and they'll all be attracted. So you might be thinking, why is this different from the last slide that we just did? Why is dipole-dipole stronger than LDF? The reason is because dipole-dipole is permanent. Okay, if a molecule is polar, then even though the electrons are going to be moving all around still, there's always going to be more on the oxygen side. So in LDF, they could really the slightly negative and slightly positive could be anywhere for that split second, and then it could go to a different place in the other split second. So this one, even though the electrons are moving, there's always going to be more around the oxygens. So these sorry, Tilly just sneezed. So these slightly negative and slightly positive are going to be attracted to each other constantly. So that makes it a little bit stronger than the LDF. And that brings us to hydrogen bonding. Now, the first thing I want to say is that hydrogen bonds are not bonds, and that is super confusing because it's called hydrogen bonding. But hydrogen bonds are an attraction between different molecules. Okay? Now, hydrogen bonds are just like dipole-dipole, except they're extra strong. So the two things you need, well, there's going to be three actually, but the two things we're looking for here are a hydrogen and then either nitrogen, oxygen, or fluorine. All right, now if you look at the periodic table and use your knowledge of electronegativity, you might notice something. You might notice that nitrogen, oxygen, and fluorine are all very electronegative. They're all at that top right corner of the periodic table. Hydrogen is not at all electronegative. It's all the way on the other side. Okay? So the reason that these are even more important than, or not more important, but stronger than dipole-dipole is because although it's still a covalent bond, it's a very polar covalent bond. The difference in electronegativity between either nitrogen, oxygen, or fluorine and hydrogen is so strong. It's so there's such a big difference between them that the nitrogen, oxygen, and fluorine is going to pull so many more of the electrons towards it. So it's the same idea as dipole-dipole, where you have slightly positive and slightly negative. The difference is it's just a little bit more slightly positive and slightly negative. And I know that's hard to kind of picture, but it's going to be not quite full positive and full negative, but one step closer. And that's why hydrogen bonding is a little bit more than dipole-dipole itself. Okay. So the diagram for this one, again, is very similar. If we do HF, let's just use HF as a bond. Don't worry about HF the acid, just HF the bond. If this was a bond, HF bond, you would know that fluorine is obviously more negative than hydrogen, okay? So, really quiet. So fluorine is going to be pulling more of the electrons towards it, and it's still slightly negative because if it was fully negative, then it would be an ionic bond, which we're going to get to in a minute. But you guys know this is a covalent bond because hydrogen and fluorine are both nonmetals. So this one's going to be positive. And then again, just like before, they're going to attract each other. The positives will be attracted to the slight negatives. Okay, so the picture again looks exactly the same. It's up to you to know that this slight positive and slight negative are more slight positive and slight negative than they were in dipole-dipole or LDF. Okay, so that's why the first slide here, I put them in order of weakest to strongest. The last one I want to talk about is ionic forces. Now, ionic forces, same basic idea, okay? They are very strong. They're the ionic forces are ionic bonds. So the reason these are the strongest is that all the other three were slight negative and slight positive. For ionic forces, they are full positive and full negative. So it's just a bigger magnet, quite frankly, if you want to think of it that way. Full positive and full negative. So here we have, let's just use salt, our favorite ionic compound. So we have Na, which is full positive. We do not have a slight sign anymore. And we have Cl, which is full negative. And then let's say we have another Na, still full positive and full negative. So the picture is going to look very, very similar in that the positives are still going to attract the negatives, but the big difference here is that there's no slight sign. So that means that these are the strongest. It's full positive and full negative. So they will be attracted to each other even that much more strongly. All right, so before we actually put this stuff into practice and we start using it, I just thought it would be helpful to summarize it. So, my guess is not everyone has been taking notes all the way along, and I get that. This is a weird setup, but I think that you should write this down. Okay, so write this chart down. You can pause the video, quickly jot it down, and then we'll fill it in. Okay. So this will be helpful on the first assignment that you have after reviewing the notes. All right, so for LDF, the rule is that it's always there. So I'm just going to write all. For dipole-dipole, two things need to be true. It needs to be covalent, and it needs to be polar. For hydrogen bonding, three things need to be true. Excuse me. It needs to be covalent. It needs to be polar. And you need to have a hydrogen and either oxygen, nitrogen, or fluorine. Okay? Now, while I'm doing this, I might as well just point out a lot of times kids think If you have any of these four, you have hydrogen bonding, but you have to have hydrogen. Okay, this is mandatory. Hydrogen must be there. And then you can have one of the other three, either oxygen, nitrogen, or fluorine. But if hydrogen is not there, you cannot have hydrogen bonding. And then for ionic, the only thing that needs to be true is that it needs to be ionic. All right. I'm going to stop this video here and then pick up on the next one with actually applying this information that we have now, figuring out what a molecule has in it and then what that means.